Okay, welcome, welcome everyone. Welcome to this session. Very warm greetings from Mercy Technologies. So, this is Monday morning, and now we are with a new topic, which is called as hashing. Okay, let's see what is our agenda for today. So, this is our agenda for today. What is hashing? So, what is a hash function? What are collisions, resolution techniques, rehashing, and why order of one, etc., etc. These look, I mean, this look confusing, or maybe these look as a big headings. But as we move further, we'll be covering all these topics, and this topic will become very interesting for you. Okay, I promise that. So have a pen and paper with you. Okay, so let's see how better we can do this. Okay, so now let me open my uh, workbook, or maybe whiteboard. I think I can open it from here. Yeah. I don't know why this is becoming very slow. Okay, so we'll be discussing about this hashing data structure. I think most of you might be heard about hash map or hash table or like hash set, something like that. But even if you don't know anything about the collections in Java or whatever it is, let's try to understand this from scratch. So I think you'll be learning about this hash map, hash set. Okay, all these things in your Java course, but there you'll be learning about how to use them. But here we'll be seeing what exactly it is, and then we can plan it in a better way. I don't know why this is struck. Just a second. Okay, so what we have done till now, our topic for today is hashing. But let me try to actually understand or make you understand like a small revision of whatever we did till now, and why are we going for this hashing, or what is its importance. Okay, let's move forward now. So let's say what hashing, right? Let me try to reduce its size. Okay, so what is this hashing? Maybe we'll be coming to its definition as we move forward. Okay, so now, but from here, let's take it further. Okay, let's take it further. So we are trying to actually understand what actually hashing is. Now, I'd like to say that hashing is a methodology or a data structure. Hash table is a data structure where you can achieve your searching capability in order of one. Okay, so your searching capability can be done in order of one, which will be in constant time. But if you see, there is like previously, until the data structure that we are learned till now, there is this balanced binary search tree, or maybe I can say the ones that we have done till now. What are those? So for array, so the searching capability was done in order of n. Okay, so then in sorted array, we used binary search, and we were able to do that in order of log n. Okay, so and then for a tree, for a binary tree, okay, we were able to do that in order of n again. And then binary search tree, we were able to do that in order of h. Okay, order of h. H can be h h is equal to n in worst case, right? H can be n in worst case. This also we discussed, right? And then we came to know one more thing, which is balanced binary search tree, and that gives us order of log n. So this is the worst case time complexities that we have done till now. So what are the time complexities we have done till now? Arrays order of n, sorted array of order of log n. This is order of n, order of h, order of n, etc., etc. But now this hashing data structure boasts that it can give your searching capability in order of one, actually in order of one, which will be in time complexity, which will be a constant time complexity. Okay, so what I want to say is this is what hashing boasts about. But let's see how this is achieved, because when you search something in order of one time complexity, then your searching capability will become so fast, and like you can use this kind of a data structure whenever maybe the interviewer asks you to make searching as fast as possible, or if he says it is a search intensive, right, which means he says that I want searching to be my top priority and make it as less complexity as possible. So in this kind of scenarios, you can use this hashing data structure. Okay, so now let's take a small example. Okay, let's take a small example. So what is my small example saying? My small example is saying maybe a question. Okay, so a question. So that question says replace print the first repeated character. Okay, print first repeated character. Okay, so what I actually mean is, for example, let's say my input is, let's say, mercy. Sorry. Okay, let's say my input is something like mercy. So my program should write the first repeated character. So what I can do is, maybe I'll take my first character, I'll start iterating and comparing my m with each and every character in mercy, right? No, this is not there, so I'll move forward, and then I'll come to e I will compare with r, c and y. So this is also not there. Then r I will compare with c and y. No. Then c I'll compare with y, and then y with y. So which means there is no first repeated character. And if you see, there will be two for loops. First for loop is for int I equal to 0, I less than, what I said is every string we can compare that to character array, right? So str dot to char array or something I plus plus. So again I can say for int j is equal to I, j less than str dot to character array, etc., etc., and then j plus plus. So for two for loops, what I'll say is if like maybe I'll say this char array of I is equal to char array of j. So in this case, then you say return, and then you will print this. So actually this code is just a pseudo code. What I actually wanted to actually tell you is to do the small simple program, print the first repeated character. First, what you're trying to do is you're trying to have a for loop, and for every character in that, again you're trying to iterate with the next character using one more for loop, and with that you were able to print the first repeated character. For example, let's say I will have an input called hash. Okay, so which means h will be compared to a, h will be compared to s, h will be compared to h at the end. So let's say capital and small both are equal. So in this case, this condition will be executed, and then you are able to print that. But in the worst case, the time complexity of this one will become order of n square, right? The time complexity of this simple program will become order of n square, because you're able to do that only in two loops. Okay, but we have to do that in a better way, right? We have to do that in a better way. But actually speaking, if you remember, we have done a program called panagram. Okay, we have done a program called panagram. So in the panagram, what we have done is we have taken one thing, right? We can do that in order of 1 second. We can do that in constant time complexity using panagram's technique. What we have done, we have taken a character array. Okay, character array, and its size is 26, right? And its size is 26 because, like, let's say we have only 26 alphabets. So what I did is as part of that program, what I did is I've taken an array of 26 characters, something like this. Okay, something like this. It starts with A and B and C and so on and so forth and Z. Okay, so if I take something like this, and let's say I have one more array or something like this, I can. So uh, I mean to say this, I can say a Boolean array. Okay, I can say a Boolean array. So what I can say is I can iterate over my input, for example, hash, or for example, mercy. And then whenever I encounter a character, I can mark that this character is already present. Okay, I can mark that it's already present. So in case if I mark it as already present, and next time when I come here and I see that it's already present, which means I'm getting a character which is repeated again, right? Which is repetitive again. So when I say it is repeating again, I can conclude that this is my first repeating character. So which means I need not have to do that in two loops, but instead I can have a separate data set or separate what you call array, which is of size 26, and then I can fill it, and then I can iterate and see if I'm able to do that. So here we can do that. Since this is done in a more efficient way, you are able to do that in order of one time complexity, right? You are able to do that in order of one time complexity. You can what do you call, you can say, no, we are doing that as 26 as a size, so how can it be order of one? I think we have discussed in the initial days that this is order of one. The reason is, you know, the actual content, or for example, even if it is 26 or 260 or 260, I mean 2600 or whatever, if the number is constant, if it is not increasing as your input increases, which means your time complexity will become order of one. Here my actual emphasis is not about the technique or something. Here what I wanted to actually tell you is, just by mapping whatever character that you have into a separate array kind of a data structure, you are able to do something in order of one time complexity, right? The similar kind of an approach, a similar kind of a thing is being done by hashing data structure. Okay, similar kind of a thing is being done by data structure. So let me repeat once more, guys. What I wanted to actually tell is, we have taken a small program. Okay, we have taken a small program to print the first repeating character. So for that, when we see the pseudo code, we are able to do that in two for loops. We came to know that we can do that in order of n square. Then we thought, if we can do it better, then we actually thought that we have already done a similar program in Panagram. So I've taken a Boolean array, or maybe I've taken an array of size 26, and then I started iterating over my character. And finally came to know that I can do it in order of one. The reason why I'm able to do that in order of one time complexity is, I'm able to map every character, or I'm able to map A, B, C, D, etc. into an array of size 26. And after that, instead of having two for loops, I can actually think of a program which can be done in a faster way. And then I can conclude that it is order of one. The reason is, my input is not increasing, right? My what do you call, my computations are not increasing as my input increases. So that's why i conclude I conclude that we can do it in order of one time complexity, and then we can do it in a better way. Okay, so this is the actual intention of hashing, guys. There are programs which are like similar to this, right? There are a few programs which are similar to this, which take two for loops, but using hashing data structure, you can do that in order of one time complexity. Okay, just wanted to ask, like, are you with me till now, guys? Yeah, now let's move forward with this concept of hashing. Okay, move forward with this concept of hashing. So what I wanted to say is, here we are able to take a string. However big the string is, our input size will become 26, because there are only 26 what do you call, characters, 26 alphabets, right? Even capital or small, we are able to map it somehow with this 26 character set, when we are able to do that. Okay, now let's say it is having symbol something like this, like for example symbol something like this, or symbol something like this, or symbol of dollar, right? In this cases also, these are called as ASCII characters, and the maximum size could be 256, right? 256, because this is how the ASCII is, like I think 128, and there is an extended ASCII which is 256, etc., etc. Here what I wanted to say is, if we are taking at as a string, if we are taking that as a string, so even in that case that becomes 256 characters, and even in that way we are able to do that in a order of one time complexity, because we are able to define the boundary that 256 would be the size of an array. But now what I want to say is, for example, let's say you have numbers, okay, 1 2 3, etc., 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 and there is until this infinity. Okay, there is until this infinity. So if you need to achieve this order of one time complexity, so what is the size of the array that you need to have? The size of the array that you need to have this one-to-one mapping is as big as it's, sorry, so it should be as big as infinity, because there is no 256 as such, because your string doesn't have a definite characters. It will start as 1 2 and 3, and then etc., etc., and it will go until infinity. The reason why I'm saying it will go until infinity is, like previously we were able to conclude that it is having 256. Now let's say using numbers I want to do something like this. I want to achieve this kind of a, I want to achieve this kind of a functionality. So let's say I want to print my first repeating character. So what I'll do is, maybe I'll try to fill up with this array and try to find out, for example, let's say there are two numbers, one and then let's say 60,836, like 60,836. Okay, because of this what happens is, it starts with one, all the others will not be filled, right? But at a particular cell called 60,836, what happens is that gets filled, which means my two numbers which I'm actually intending to do that will have the size as big as infinity, and like most of my array will be not filled, will be not filled, right? So but even in this case what happens is, we are able to do that in order of one time complexity. Okay, we are able to do that in order of time complexity, and that is something which is good, because that is our intention, right? The actual intention of going for hashing data structure is only to achieve that in order of one time complexity. But it's foolish way of doing, right? Like if you are able to achieve something in order of one, but you are consuming so much of space, and like, which means you're not doing something good, right? You should do something good, because there should be a balance between two things, right? Let's say you're achieving something in order of one time complexity, which means you should even be thinking about space also, right? Because the space is growing indefinitely, right? In this approach, the space will always be order of, like it will be infinite, like you do not have a finite place of ending to it, and that consumes a lot of space, and that's not a good way also. So how do we do it? So which means instead of having uh, an array as big as infinite number, so we need to have an array which is having, which is having some finite number. So that's why here comes a concept. So here comes a concept of hashing. Okay, here comes a concept of hashing. Till now we have done this hashing only. Hashing is nothing but having a function h of x is equal to x. Okay, h of x is nothing but the number that you are trying to find, and then this capital X is nothing but, I can say, this is an index. Okay, so here in our previous example of having infinite number of array, what will happen is, for example, let's say I should say h of 60,000. So what is my input? Let's say my input is 60,836. Okay, I can say 60,836. So which should give me the index number. Previously we were having one-to-one mapping, and this also will become 60,836, right? Which means we are having one-to-one mapping. Like when I say h of x, when I passing this number to my h or hash function, it is giving me a number, and that is the index of that array. But here what we concluded is, this hash function is improper. right? This hash function is not good. This hash function is not good. So that's why we need to do it somewhat in a better way. So that's why we need to devise a better hash function. So what is a better hash function, guys? Better hash function is nothing but it needs to have a mapping something like this. Maybe I'll be showing you what or maybe I'll straight away show you this thing. Yeah, hashing, right? So yeah, hashing is nothing but here, instead of having so big number, we will be having something like this. Assume that your array size is not infinite, but assume your array size is having only 78 or maybe only 8 slots. This number or the size of the array you are deciding. Okay, let's say you are assuming that you are having only 8 slots. Okay, so which means, let's say I want to pass a function which I said h of x is equal to capital X. Now my hash function will be becoming something like this. I'll show you my hash function, how my hash function looks. H of x is equal to capital X percentage n, right? This n I'm assuming here to be 8. So whenever a number comes, for example 60,836, I need to store this. What I'll do is I will get a reminder by doing this percentage 8, and maybe I'll be getting a number, and I'll be putting this number into that particular index, right? The same thing we have done here. If you see, I want to insert 36. 36, what I'm trying to do is, instead of inserting that at 36th position, I'm trying to do percentage 8. When I do percentage 8, 8 fours are 32, and then 4 will be my reminder. So at 4, I'm inserting this 36, right? And then I want to insert 18. Okay, I want to insert 18, and I did percentage 8, which means 8 twos are 16. I am getting a reminder of 2. Okay, so which means at second position I'm inserting 18. Okay, 0, right? I'm inserting, right? 72 I'm inserting, and when I do percentage I'm getting 0, so which means I'm inserting 72, right? And then 3, so the same thing I'm inserting at, 43 I'm inserting at position number 40, position number 3, and then 6 I'm inserting at position number 6. Okay, so I'm inserting at position number 6. So using this hash function, using a small hash function, what I'm trying to do is I'm trying to reduce my infinite size of an array to some finite number, and that finite number I'm making that as 8. I'm making that as 8 just by having a small hash function. Instead of having one-to-one mapping, right? I'm trying to have a hash function. That hash function is giving me a reminder, and that reminder will be the index, and I'll be inserting this 36, 18, 72, 43, 6 based on my hash function to those corresponding indexes. Okay, so using this, what happens? The size will be less, but you are able to put that, yeah, Tanmay, I'm coming to that. Okay, so you are able to put that, right? Now good. So what happened? There was one problem that came to us. What was that problem? That problem is order of, like, we are able to do that in order of 1, but we came to know space is something that is causing us a problem. Okay, space is something that is causing us a problem. So with this, what we did is we have done hash function. Okay, so which means we are again able to do that using hash function. But if you observe our example, guys, let's say I want to insert uh like, now I want to insert 4. Okay, I want to insert 4 percentage 8 will be giving me 4 again, but 4 is having 36 in it, right? 4 is having 36 in it, which means like, in a position that I have calculated using my hash function, there is an element that is already there, right? There is an element that is already there. I have to come out of this kind of situation, but this kind of situation is having a name, and that is called as collision. Okay, my input is already colliding with the one that is already present. So this is called as collision. Okay, this is called as collision, which means here hash function we are able to do that, but again collisions, right? Okay, collisions, how to do because of this collisions. Okay, now maybe I'll try to open my next example over here. So okay, what is that? Collisions, right? Whenever you get a collision, something like that. So I told you until 15, or maybe so until 15. So yeah. So here until 2 we were able to we were able to do that in a proper way, in a proper way. Okay, until 2 in the sense like until 6 we were not having collisions. But let's say at a particular point when I'm trying to insert 10, I'm having a collision, right? I'm having a collision, 2 is already having. So that's why what happens is whenever there is a collision, or maybe instead of directly storing that as a number, so here there will be a linked list which will be formed. Okay, there will be a linked list which will be formed, something like this, right? Something like this. What is that? For example, let's say there is, okay, there is something like this, and I'm having a collision, let's say at a particular bucket called 1. So instead of storing it, so I'll be having something like this. Okay, I'll be having something like this, etc., etc. 5, 9, 11, or whatever. Whenever you get a collision, you will be inserting that as a linked list. Okay, you'll be storing that as a linked list. Just a second. So you will be storing that as a linked list. Okay, great. Now, yes, we were able to do that. And what is the name of this, guys? There is a name for this. Okay, there is a name for this. There is a name for this, and maybe I'll be discussing about this name. This is called as open chaining. Okay, whenever there is a collision, you are able to form a chain. Okay, so there is a rule for this also. Okay, there is a rule for this also. What is that rule? This chaining is nothing but this is called as chaining. Okay, chaining. Okay, or this is called as open addressing. Okay, so here what I wanted to say is whenever you come to this kind of a situation, so instead of directly having a linked list, here you need to have something like this sorted linked list. Sorted linked list. The reason why you want to have a sorted linked list, so for example, let's say we are trying to insert a new number which is already there. We need to sort it first and then we have to insert. The reason is something like this. The reason why we need to have sorted one is, so instead of like sorted array or sorted linked list, whatever we can say, instead of searching that again in searching that again, if you search a normal array, it will be done in order of n. But if you search a sorted array, that becomes, you will get something in order of log n. The same process, that's the reason. So instead of straight away inserting something, you will be inserting that into a sorted linked list. Okay, sorted linked list. So something like this, that's fine. Now we are able to do that in open addressing platform, and you are able to do something like this. So let's say I want to search for 11. I've not taken the straightforward example, guys, but here what I wanted to say is, let's say I want to search for 11. So I'll be doing that. I'll be giving this 11 to my hash function. Okay, let's say h of 11. Okay, let's say my hash function is pointing me out to this index called 1. I'll go to this index, and if I find that index is 1 and then it is having a linked list, then what I'll do is I'll try to search, is 5 my 11 or not, like is 9 or is 11. So in case I find it, then I'll go here, then I'll return it, right? So then I'll return it. So instead of having one-to-one function, what we did is we thought we'll be having a hash function which will be pointing various other numbers to a particular thing, but we came to collisions, right? Here we have achieved this using open addressing. Okay, open addressing. That's good. That's good. Till now so good. Right? So what I wanted to say is, here there is again a problem in this open addressing. So what is that problem? Uh, you have a hash table. This is called as, okay, let me come to the terminology, guys. This is called as I'll be using a different color. Okay. Um, yeah. So this is called as hash table. This is called as hash table. Okay. Every particular index, or you can say this box, this is called as bucket. Okay. This is called as hash function. Okay, this is called as hash function, right? Here what I want to say is like open addressing is nothing but you have a hash table, but to that hash table you are linking a sorted linked list, right? Which means the address space is not within this hash table, right? So your memory is occupying even more or out of this hash table also. That is why it is called as open addressing. But let's say instead of having it out of my hash table, let's say I want to have it somewhere inside me only. Like what I want to say is I want to have something, I want to have whenever a collision occurs, instead of making that go outside my hash table, I want to insert into me only. The reason why I'm saying is, for example, let's say my hash table is of size 8. Okay, all my numbers that I'm inserting are giving me the same collision, which means even though there are empty spaces in your hash table, you are pointing that to an external linked list, and you're trying to grow that in some other possible way, which means instead of growing it in this direction, you're growing it in this direction, which means your total data structure will be increasing. It will be increasing in this way, increasing this way, and increasing in this way, which means again that becomes an order of n square or whatever that becomes a matrix. Okay, that will give you a separate problem. Okay, so like I'm not going into deep of those, but what I wanted to say is when you have empty space in your hash table, why not use that? And why do you go for going out and say something like this? So there comes, so which means open addressing, right? Here we have done open addressing again has a problem. Okay, open addressing again has a problem. So what is my open addressing saying? Space. Okay, so now open addressing is has a space problem. Now let's say I want to have one more technique. Instead of using an external linked list, I want to use my internal hash table only, internal buckets only, which are free. So that's why I have something, an operation or maybe a technique called closed addressing. Closed addressing. Okay, so using this closed addressing, yes, your space your space will be something like which is like which will be saved. Now maybe I'll show you an example what closed addressing means. Okay, so what closed addressing means. Yeah. Okay. So what I want to say is, for example, let's say on our left hand we have an array which is already filled, right? And we have done the size of our hash table is 8. You are adding 10, 5, and 15, right? Now you need to, this is a filled one, the left side one is a filled one. Now you want to add keys 10, 5, and 15. So what is your number 10 saying? Number 10. So you need to insert that in 2, but in 2 there is already 18, right? There is 2, there is already 18. So which means instead of right, you want to insert 10, right? You want to insert 10, right? But like what is the next available space for me? Okay, what is the next available space for me? The next available space for me is only 5. Okay, next available space for me is only 5. But because like after 18 I do not have any empty space. But what I'm thinking is, like, if there is empty space, why not make use of that instead of having that as an external linked list? When I have an empty space, why not make use of that? So that's why my closed addressing will be having something like this. So what is that? My hash function will become something like this. H of x is equal to x. Okay, so which means h of x is equal to x, but h of x is equal to x plus I. Okay, so what is my I is equal to 0, 1, 2, 3, so on and so forth. Okay, what will be its size, etc., we'll be discussing. So what I want to say is h of x is equal to what do you call okay, x percentage n x percentage n plus I, which means I have done this percentage over here in my calculation, and after that I'm trying to find plus I, which means I'm trying to move one index further. Like for example, let's say I want to insert 10. Okay, insert 10, I got 8, I got 2 as my index, but 2 already has 18, so that's why I'll add 1 to my index, which means I'll add 1. I'll see 43 is there, so don't insert. I'll add 1 again, 36 is there, so don't insert. I'll add 1 again. Oh, now 10 is there and it is empty, right? So which means it is empty, and at fifth index I'm able to use that, right? 10. So the same thing happens with 5 as well. Okay, I mean same thing happens with 5 as well. I want to insert 5, but 5 is already having some number which is 10, so maybe I'll try to add 1 1 1 1, and finally I try to find that 7 is an empty space, so which means I'm trying to insert it over here, etc., etc. So in this way, what am I trying to do is I'm trying to use the empty spaces that are there inside my hash table only, and I'm not trying to have one more array which is going outside or external. So which means I'm trying to use my hash table without any spaces. I'm trying to do the maximum space utilization. Okay, I'm trying to do the maximum space utilization. So we'll be coming to the other case, but here what I want to say is, instead of making that as an external linked list, we are trying to modify our hash function to do something like this: h of x is equal to x percentage n plus I. Okay, this is something like this. Okay, but now here there is a problem. Okay, there is a problem in the sense, I don't say it's a problem. So this is called as, actually speaking, you are not able to find your empty space, so that's why you're hopping. Like, I'm trying to see if next is empty, next is empty, next is empty, next is empty, this kind of a thing. So which means I'm trying to do nothing but searching. The searching is called as probing. Okay, probing. So which means I've done a program probing. Open addressing has a concept called probing. Probing is nothing but searching, and probing is having probing has two things, guys. First thing is linear probing. Linear probing is nothing but adding one index and trying to find if there is any empty space or not. Okay, linear probing is nothing but trying to find if some empty space is present or not. Same thing we have done over here. So what we did is, when we encountered an index of 2, we found that there is 18, and then we tried to increase or add I to it, add 1 and add 1, add 1, add 1, add 2, add 3, add 4, because I becomes 0 1 2 3 4 5 6, etc., etc. So, and then we came to know that 5 index is empty, and then we have directly inserted it over there. So using this technique, we are able to do something just by how we are searching by adding I, which means 1 2 3 4 5 6, etc., etc. Now, by following this technique, there is a problem, guys. The problem is, for example, let's say you have a hash table, something like this, and let's say whenever there is collision, you'll be inserting it one above that. For example, let's say there is a collision over here, and let's say there is a number over here, and finally what you'll do, you'll try to add 1 and you'll insert it over here, and then again there is a collision, let's say you try to insert it, again there is a collision, you try to insert it over here. So what happens is, all the numbers or all the collisions that had are very near to each other, so that is nothing but cluster. Okay, so that is nothing but a cluster. So which means, because of linear probing, what happens is, you are trying to form something which is called as a cluster. Okay, let me remove all this. Okay, so what is the problem with your linear probing? You are able to do that in a proper way, but here there is a problem which is called as cluster. So here there is a problem which is called as clustering. Okay, which means you need to somehow remove this clustering. So that's why, instead of having this plus I, which is linear probing, let's say I have a hash function, something like this. So what is that? H of x is equal to x percentage n plus I square. So instead of which means I is equal to 1, 2, 3, so 0, 1, 2, 3, etc till n. So what I want to say over here is like, which means the I value will become 0 or then 1 or then 4 or then 9, etc. What I want to tell over here is whenever you find a collision, instead of trying to search in the next bucket, you'll be searching in the square of the next bucket, right? Maybe I'll show you an example for that. So what is my example saying? My example says something like this. My fourth one, yeah. Okay, so the same thing. So here you already have a filled hash table. Now you are trying to insert something which is 89. Okay, 89 has 9. Okay, 89, yes, you are done. And then in 8 you're able to insert 18. Now let's say you try to insert 49. Here the size is 10, guys, in this example, but that's fine. That is not breaking our concept. So let's say you're trying to insert 49, but 49 in this index called 9, you already have 89. So that's why in your first attempt you'll be incrementing that with I square, which means 1 square. Okay, 1 square. But here if you see in my 9, there is a 49 already. Okay, so which means, sorry, okay, so there is this 49 already, right? I came to this 49 already. When I came to the 49 already, that's fine. This is an empty space for me, so that's why I inserted it over here. Now let's say I want to insert 58, which is giving me 8, but 8 is having 18 in it already. So which means I try to do one square. 89 is already having this. And and then and then what I want to say is, what I want to say is, here there is one important point that you need to take care, guys. What is I value? I value is nothing but, for example, at a particular point called 58, which means at a particular point called 8, 8, which means 8 is something that is already having. So 8 plus 1 is having a space already, is not having a space. So which means I is equal to 1, it's not working out. I is equal to 2. When I is equal to 2, it is having 49 in it. It is not working out. When I is equal to 3, yes, it is having an empty space. But instead of inserting that in I is equal to 3, which means a third index, I will do 3 square, which means 9. So I'll be counting. So what is the point? I'll be counting 9 from here. 1, 2, 3, 4, 5. So what is that? We have to insert 58, right? So instead I'll be counting 1, 2, 3, 4, 5, 6, 7, 8. Maybe the counting is improper. What I want to say is like 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah, if you count 9 times from 18, okay, if you count 9 times from 18, then you will be coming to this index called 58, and you are inserting. So which means what I want to tell you over here is, you will be moving that into I square times. What is I square? Whenever you encounter a collision, you try to find out if next bucket is empty, next bucket is empty, next bucket is empty, which means you do a linear probing. So after you do a linear probing, you will be coming to know what is I, and you will be squaring that, which means 3 square will be giving you 9, and from that index you will be adding 9 spots, and for that 9 spots you will be finding a space and you will be inserting. Same thing happens with 69 also. Maybe you can see and you can practice and you can see. What I want to say over here is, because of this, what happens, instead of having all my elements next to next, I'll be removing my clusters, right? I'll be having them towards like more spaces, right? There will be huge gap between those two, which means you are efficiently using your hash table, right? Which means in this way you are trying to avoid clustering, right? So which means linear probing is having a problem called clustering. So in this way you are doing that by I square, that is called as quadratic probing, something like this. And clustering, so clustering, you are able to do that because clustering, you are able to achieve that clustering, or maybe there will be clustering, but they will not be as much as the linear probing, right? So in that way, you are able to even remove this clustering also using quadratic probing. Okay, quadratic probing, right? Are you with me till now, guys? Are you with me till now? What we did, why we did, etc., etc., all these things. For 58, why not possible in second attempt? So what is that? 58. Maybe I'll open that. So what is my, sorry. For 58, why not possible in second attempt for 58, right? So what is 58? 58 is nothing but it is giving me an index of 8. Okay, index of 8. Okay, index of 8. Okay, index of 8 already has 18 in it, right? 18 in it. So what I came to know is 18 is already having a number. So what I do, I add 1, right? I add 1. When I add 1, I go to an index 9 and I find that 89 is already there. So which means I'm not able to fill it. Now I add 2 and I come to 0 again. I again came to know that 49 is already there. And then I add 3. Okay, I add 3 and there is this one which is empty. So as part of my quadratic probing, instead of inserting that at an empty position, so I'll be counting that, right? 3 is my count, right? I'll be doing count square, which means 3 square. So to that 3 square, which means 9 from 50. So I'm able to do that from 18. I'll be counting 9 spots and then I'll be inserting instead of doing that in my second attempt, because second attempt will be giving me this what do you call it, 49, which is already there, right? So that is why it's not possible then. Understood? Yeah, we will not be adding 4, we'll only be adding 2. Okay, fine, that's fine. Okay, there's a confusion, no problem. Okay, now here we are able to do that. Okay, now you will be getting a question, right? What happens when my total hash table gets filled up? Okay, so here you will be having that doubt. Okay, what happens when my total hash table gets filled up? Also in our case, so it is getting filled up in this way. For example, at a particular point, all the empty spaces also will be filled, right? At that time, what will happen? At that time, there is a concept called rehashing, guys. So when you say rehashing is nothing but, let's say your size of the table is now 10. Okay, maybe you'll be taking the size of the table as 20 or 30 or whatever. Again, to that 20 or 30, you will be having a hash function, right? Now hash function, instead of doing percentage 10, you'll be doing that percentage 20 or percentage 15 or percentage like 16 or whatever. So there is a concept of having that to the next prime number. Like I'm not going deep into those conditions, but what I wanted to say is, uh, in this kind of situation where your table is totally filled, you will be having an option or having a concept of rehashing, where you compute your buckets again, and you'll try to fill up all those elements one by one. Okay, so that is called as rehashing. Okay, now we have done something like this, but there is one more technique also. We have done linear probing and quadratic probing, but there is one more concept. This is not that greatly used, but this is called as double hashing. Okay, so what is double hashing, guys? Double hashing is nothing but, for example, let's say whenever you have a collision, something like this, right? 8, and you have a I mean, I'm just going through an overview of this. What it says, I want to insert 49 percentage 10, and 9 is my collision, right? 9 is my collision. So uh I'll be doing something like this. My collision is having two hash functions in it. Two hash functions. So what I want to say is, nine is having a collision, right? My hash function is h of x is, right, I mean, say h1 of key is equal to key percentage 10, and there is one more hash function.
Okay, there is one more hash function. What I'm trying to do is 7 minus my hash function, 7 minus key percentage 7, etc. So why did we come to this second hash function, or on what basis did we conclude, etc., etc.? This is a concept, guys. Like, instead of having a single hash function, whenever you find a collision, you can have one more hash function that is called as double hashing. Maybe you can actually go through this example also. I'll be giving you that as part of our notes or whatever. Here, the actual intention of telling you is, instead of having a single hash function, whenever there is a collision, you may have one more hash function, and that also will reduce clustering, right? The reason why we had this quadratic probing is to remove clustering. Same thing, this double hashing also will reduce the clusters as much as possible by having a second hash function, etc., etc. So again, we discussed in one more point, whenever we have a hash table which is full, there is a concept which comes into our picture, that is called as rehashing. Okay, so here maybe let's try to find out the conclusion points, guys. This is what hashing actually means. We try to learn something new today, so maybe let me conclude. Okay, or let me try to give you a summary of whatever we did till now. So what is our hashing? The reason for going for hashing is, we have taken a small example, and that small example was to find the first repetitive character. We came to know that we are able to do that in order of n square, but we try to do that in a better way, better searching, better capability. We came to that the reason why we are using two for loops is because we need to search it, right? Then we came then we actually revised what are the different searching capabilities that we have done till now. We came to know that the best searching capability that we have done till now is either a sorted array or a balanced binary search tree, which gives us order of log n. But can we do that even in a better way? So in that way, we came to know this capability, or this function, which is called as hashing. So hashing, so which means, so what is the reason for going this hashing? uh, Okay, the reason for going to this hashing is hashing. So this gives us order of one time complexity. Okay, this gives us order of one time complexity. So what is this hashing function? Let's say I have h of x is equal to x. All right, so in this way you are able to map it. So what happens because of this? Because of this, there is something called too much space. Okay, too much space. So how did you reduce this too much space? How did you reduce this too much space? You uh, you did reducing of this too much space using a hash function or something like this. So what you did is h of x is equal to capital X percentage n, right? N is nothing but space. So with in this way you are able to do something like this. Okay, you are able to do just by having this one. Now again there is now again there is a problem here. This is nothing but this is called as many to one relation, guys. Many to one. So what is this many to one relation? To one particular key, there are many numbers which are linked to, that is called as many to one relation. That's fine, but here again we encountered a problem. So what is our problem? That is called as collisions. Okay, so collisions. So for collisions, again there is a collision. So what we did for collisions is, like, we did something like this. We did two techniques, which is open addressing, right? And then again we had something like closed addressing. So in closed addressing also we had linear probing, and then we had quadratic probing, and then one more we had is double hashing. Okay, I think because of the space constraint, I'm not able to do that, or not able to write that even in a proper way. So what I wanted to say actually here is, we came to hashing, we came to know that we can do that in order of one. Then we had a hash function, came to know that there is too much of space, and then what we did is, we can do something like this, because h of x is equal to capital X percentage n. But here we came to know that there are collisions. So for that we had this open addressing. Open addressing is nothing but having a linked list, or maybe sorted linked list. sorted linked list. So here we came to know that sorted linked list is again a space. Okay, so now we came to closed addressing. Closed addressing we came to linear probing, closed addressing we came to quadratic probing, and then closed addressing we came to this double hashing. So all these things we came to know, and finally we came to know what are the different advantages or disadvantages in various aspects. But here the reason why we are trying to do all this is our actual intention is to get this order of one time complexity, and that's it, nothing else. So after getting that, we try to dig even more, even more, even more. No need to complete. Yes, 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 yes. Okay, okay, okay. That's fine. This is a conclusion, guys. This is a conclusion that I wanted to say. So here there is open addressing, and we are having sorted linked list. Here also we have a space over here, and then in closed addressing we have linear probing, quadratic probing, and double hashing. So all these things, or maybe I'll try to write it in a better way so that maybe you can have. Mm, okay, closed addressing. Okay, so closed addressing was having linear probing. Okay, and then we came to know that there is quadratic probing. Okay, and then we came to know which is called as double hashing. Okay, linear probing was having a problem of clustering. Okay, linear probing was having a problem of clustering. To reduce or to avoid this clustering, so what we did is we came to this quadratic probing, and then we came to know this double hashing. Maybe there will be a questions on, is quadratic probing better than double hashing, all this, etc., etc. These are, like, I mean, too much into computer science basics, guys. These are not required as of now, but here, yeah, again, maybe I'll try to write this. So just a second. Okay, so here we had a space problem. So to reduce sorted linked list, so sorted linked list, so because of this we have open addressing space problem. So because this space problem is a problem with our open addressing, then we came to closed addressing. We came to know different what do you call, the probing techniques, etc., etc. So this is a summary, guys. This is a small bit of summary. Like let's say you want to prepare for something, etc. You can see this, or you can take a screenshot of this, and then, like, you will be, like, revising it as fast as possible. Okay, let me go to my presentation, my previous presentation, and maybe we'll see did we miss something or not. Okay, here it is. So what we did, our agenda was to find out what is hashing, we did that. What is a hash function, did that. Collisions, we did that. Resolution techniques, we did that. What is rehashing, we did that. Now we'll come to this part, how did we get order of one time complexity. Okay, now what is the problem, maybe we did something like this. We finished. Okay, this one maybe I missed it. So what is that? Hashing is nothing but you have a key, you put that into a hash function, and you'll be getting a hash value. The same thing that I told, this h of x, etc., etc. Right? For example, 89 is your key, and let's say the size of your hash table is 10, and when you day 89 percentage 10, you'll be getting 9 as a reminder, and then that reminder, you'll be mapping that to a bucket value called as 9. The same thing is discussed over here. Okay, so I think we in the collision resolution techniques also, yes, we were able to do this linear probing, quadratic probing, and double hashing, etc., etc. So we were able to do all these parts. So all these parts. Now here you may be giving a question, or maybe you may be asking a question. So we are doing all these things, right? For example, let's say I want to search, right? I want to search. Here the reason why we did all this hangama is only to search it in order of one time complexity. Okay, but here again there is a problem, right? Again, there's a what is that problem. For example, let's say there is a collision, etc., and then I want to search. I cannot straight away search order of one. I cannot directly go to that index and get that, etc., get that straight away, right? So maybe something like this I can say. So whenever I try to search 18, so what I should do is, maybe I should calculate that h of x, come to this position called 2, and then I will be going to that 18 eventually, right? Not straight away. I will not get in order of 1. So we are doing some computations, or maybe we are trying to search it in a sorted array. That becomes an order of log n, right? How do we conclude that it is having order of one time complexity? Okay, this may be a question, but the answer for this is right, maybe even in this open addressing also there will be a threshold, right? There will be a threshold, or there will be a particular point where you can say the maximum length that my linked list can grow is, let's say, 5, or maybe I have a finite number for that also. I cannot say it can grow infinitely. Okay, it can grow infinitely, it's nothing like that. So I will be having some finite number. So when you try to search in a finite number, even though it is order of n time complexity, so what I want to actually say is, when you have a finite number, the searching will be done in order of one time complexity only. The reason is, like, your input will not be growing, your what do you call, your size or number of steps of computation will not be growing as per your input. Okay, even though your input is, let's say, 1 lakh, right? Even though you got a collision, okay, so the maximum limit that you are putting is, let's say, is 5, right? It will not cross 5, so which means it will not be order of log n, right? It will be in order of 1 only. Even though there are small computations, as I told you, we will be ignoring that. The same example I think I have given, like, you went to a shoe shop and you are trying to buy shoes and socks. When a friend of yours comes and asks, what are you buying? You will say you're buying a shoe. You'll ignore socks, because in comparison to the value of shoe that you are buying, you will not even consider that you have bought a socks. So similarly, when there is a huge input, the small computations you'll be including, the constants you'll be including, I mean, you will not be including. And so in that way, what you actually conclude is, like, this small computations will not be into order of n or log n, but they will be into order of 1. So this is the point, guys. I think we have completed our agenda. Our agenda is, like, all these 6 points have been completed by now. So this is hashing data structure for you guys. Like, did you follow me till now?